Uh-huh.
Okay. So welcome back to Compass Lecture. We're so glad to see everyone here, and I'll be introducing the speaker today. So Mengke is a postdoctoral researcher in physics department. Before that, she finished her PhD in physics at Clemson University, working with Professor Bradley Mayer on nuclear astrophysics. So she's going to give us a talk on heavy elements.
Thank you for the nice introduction. And yes, that's the topic of today, from merger to matter and understanding the formation of heavy elements. Um, this talk, I think, will be very chill. And if you have any questions when I'm giving the lecture, feel free to interrupt. We can discuss. And okay, let's get started. And I know she has nicely introduced me. I would like to introduce myself again, but in a different version. And for here, that's about me. I'm curious from small to vast. And what does that mean? It means I enjoy, not enjoy, I've always been fascinated by the tiniest building block of the matter, like protons and neutrons living in a world measured by femtometer. And at the same time, I love looking at the sky and wondering how the universe came to be. And nuclear astrophysics is the field those two curiosities meet. So, and that's what we will focus on today. Basically using neutron-rich nuclei to understand the formation of the heavy elements. But I will not specifically focusing on the part I'm working on, but broadly introduction about the formation of the heavy elements. And okay, that's another slide about myself, but that's fine because I don't know if there is an introduction or not, but just a journey of my academia record. And I graduated in 2018 in China. I come from China originally. And then I went to Clemson for a PhD program. And in the middle, I got my master's degree there. And after that, I did 2 summer interns at Los Alamos National Lab. And in 2023, end of 2023, I got my PhD degree. And then I'm a postdoc here as an N3S fellow. Now we will go to the talk today, and that's the roadmap. I will start with the formation of heavy elements. We call them nucleosynthesis. And once we have an idea what the heavy elements are made in the universe, like from lighter nuclei to the heavier nuclei, and I will focus a little bit more on the rapid neutron capture process, which creates the heavy nuclei. And heavy here, I mean heavier than iron. And then, because that's nuclear astro, once we have an idea about what astrophysical condition that process can happen, and I will talk about the nuclear physics, and as using nuclear masses as an example to demonstrate how that can affect our understanding for the formation of heavy elements. And then in the end, I will show you how the astrophysical observables can help us to constrain our understanding for nuclear physics. Okay, now let's get started. And I always like to start with this version of the periodic table. And I guess you know all of the elements, but for here, different colors stands for different astrophysical origin. And for example, from the lightest elements like hydrogen, helium, and a little bit lithium, they are formed in the very beginning of the universe by Big Bang nucleosynthesis. And for beryllium and boron, there is no direct way to form those nuclei because when the helium capture neutrons, those are unbound nuclei. And the only way to form those two nuclei are by cosmic fission, and which means the high energy cosmic ray will break up the heavier elements from the later and then break up to those lighter nuclei. So the abundance of those two are really low, you will see later. And then starting from carbon all the way to iron, those will form in the inside of the star by the stellar fusion reaction. And I will also demonstrate how this works in details later. For everything that's heavier than iron, like all of the orange and yellow parts, they are forming in a completely different mechanism, which is the neutron capture process. The reason is for the fusion reaction all the way to iron, that's exothermic reactions. That means when you combine two particles or two nuclei, you release energy, and the nature prefers to stay in a lower energy. But for everything higher than iron, when you put two particles together, they don't release energy. That's endothermic. you need to add to absorb some energy to form that. So nature doesn't want that. But the neutron capture process, like the different mechanism, if you capture a neutron, it will still release energy. And so the nature prefer this way to produce the heavy elements here. Okay, and that is like different way to form different elements. And on the right figure, that is the observed abundance pattern in our solar system. And on the y-axis, that's abundance. On the x-axis, that's mass number. And like here, that's hydrogen and helium, and lithium, beryllium, and boron is very low. That's what I said here. They form by cosmic ray fission because there is no direct way to form them. And for everything that's highlighted in orange part, that is the stellar fusion reaction. They form in this region, but for everything that's highlighted in the pink region, that's the neutron capture process that's forming those elements. And you might wonder, how do you get this abundance pattern here? How do you observe them to have those information? And we have different ways to do that. But the main information we got are from two sources. And one is from our solar, like from the sun. The solar's photosphere, we can get the absorption spectroscopy data and try to analyze what atoms are there. That's one way. The second way is to, sorry, I think it is here. Yeah, from the meteorites, they also contain the information, or I should say from the solar, we can get the elemental abundance information, but from the meteorites, we can get the isotope abundance information. Isotope here means you have the same elemental number, but you have different neutrons. That's different isotopes. Okay, and then from here, I will focus on the lighter nuclei here first before I dive into the heavier one. For the lighter nuclei, as I mentioned, they are formed by stellar fusion reaction, and that's a massive star. Let's say like larger than 8 solar mass. And the stable state for a star is maintained by two forces. And one is the gravity drag everything inwards. And the repeating force is the radiation pressure from the inner part. That is the fusion reaction. In the early time of a star, that's all of the hydrogen there. And hydrogen get together to form helium. That is the first part of the fusion reaction. And that also lasts for like 7 millions of years. That's the longest phase. And if you run out of hydrogen, there is no pressure pushing forward. And due to the gravity, they will crash again. When you crash, you heat up the material. When it's hot enough, that will ignite the helium. And that's when the helium started to be the fuel. And then through triple alpha reaction, which means 3 helium particle converts to a carbon, you start to form carbon. And similarly, if you run out of helium, you will start to fuel carbon and all the way to iron core. So that is how, by different shells, you can form heavier and heavier elements. But for this mechanism, you can only go up to iron. Okay, why is that? Why iron is the ending point for the fusion reaction? And that's because the nuclear physics. And here, that's a binding energy versus mass number. Binding energy means if you have certain amount of neutrons and protons, you put them together, and then you release some energy. And from the lighter nuclei here all the way to the peak, which is iron, it has the largest binding energy, which means that's the most stable nuclei. If you combine to iron, you release the maximum energy. So when you fusion all the way to iron, oh, I'm stable, I don't want to do anymore. And that's why for the fusion reaction, they all ended at iron. And for everything that's heavier than iron, like in this region, and since fusion reaction doesn't work anymore, we need to find a different mechanism. And that will be the neutron capture process. You cannot absorb a large particle to form a heavy nuclei, but you can still capture smaller neutrons to gradually build up your mass. Okay, for the neutron capture process, which will be, okay, here that is the iron abundance, which is the first peak of the R process elements. And everything after here, like if you see kind of green color, and the solid line here, that's the R process nuclei, and the solid line, that's the S process nuclei. And R and S here means rapid neutron capture or slow neutron capture. Those are two processes, and one of them is responsible for creating roughly half of the heavy elements in our universe. And okay, I will show you the difference between R and S elements in the next slide. And the R and S were rapid or slow. Yeah.
This has to about the iron. So is that specifically for any sort of isotope of iron, or is it like a specific isotope where we have the most stable nucleus?
For iron 56 is the most abundant, most stable nuclei. You might form like iron like 56, that's 26 neutron, 26 proton, 30 neutrons. You might have more neutrons like iron 60 or iron 65 or something. They are not as stable as 56, and they will either decay to the stable nuclei or they will decay, but it will take some time depending on the half-life of the isotopes. Okay, now we will focus on the neutron capture process, which is creating the heavy nuclei in our solar system. That's also in general true. Even in the universe, you want to form the heavy nuclei, you also need to go through those neutron capture process. And here you might notice the solid one always has a peak that's earlier than the dashed one. Similarly for here, those peak and this peak, those are governed by nuclear physics. And if we have time, we can talk about that. Okay, now I will show what's the difference between rapid neutron capture process and slow neutron capture process. And slow or rapid, that's relative to beta decay. You know, as I mentioned, if you are in iron, you capture a neutron, capture a neutron, capture a neutron, you're still in your own isotopic chain. You are not going upwards to be z equal to 50, like nickel. You cannot go up by z, you can only go up by n. N is the neutron number. How can you go up by elemental number? That's by taking a beta decay. A beta decay is converting a neutron to a proton. So you can go from this isotopic chain to the next isotopic chain and go upwards again. That's the beta decay process. And why we care about beta process is because that's the quantity we compare with. If your neutron capture process is so much faster than beta decay, it will continually capture your neutrons all the way in your own isotopic chain. Sorry if I didn't explain. On here, that's a nuclear chart. On the y-axis, that's proton number. And on the x-axis, that's neutron number. For the rapid neutron capture process, because that's rapid than or faster than beta decay, you will go on this horizontal chain. That's one isotopic chain before you hit the neutron drip line. Neutron drip line is if you capture another neutron, you don't release energy anymore. And that will be the end of your isotopic chain to capture neutrons. And then you will take a beta decay and go up by z for one number. And since your neutron capture rates are so much faster, you will continue to capture neutrons. And like the R process is kind of working in this part. It's always staying in very neutron rich part. But for the slower neutron capture process, those black ones, those are stable nuclei. And since the slow neutron capture process, they are slower than beta decay. They will stay their own position. If they have a the time scale for neutron capture might be millisecond, but for the time scale for a slow neutron capture might be years or 10 years. You wait for such a long time, you capture a neutron, but the beta decay will quickly take you back to stable nuclei. So the S process is always along this stable line, but for the R process, that's always in the neutron rich part. And so how to make the neutron rich part to get to the stable nuclei is when they run out of neutron, they just wait for decay, and then they all decay back to form the stable nuclei here. As I mentioned, there are two peaks when you look at the abundance pattern, and the R process peak is always on the left. The S process peak is always on the right. That means the S process peak is a little bit larger in the mass number. The reason is you see here is a closed shell. Closed shell means you're more stable than the other nuclei, like people or material tends to stay here. And for the R process, if you have same n number, your z number is roughly here. But for the S process, you have the same n number, but you have a larger z number. When you add them together, the S process particles always have a larger mass number than the R. That's why the peaks are separated. Okay, that's the S and R. And for the R process, as I mentioned, the neutron capture rates timescale, the neutron capture timescale is like millisecond or even less than millisecond. It's super fast. And that means you need to happen in an environment you are surrounded with many, many neutrons. Like if I remember correctly, 10 to the 23 neutrons per centimeter cube. That's very, very neutron-rich condition. And you might wonder, yeah.
Can I ask a question?
Sure.
So here the boxes are stable elements.
The
ones that are.
Yeah, the black ones are stable.
But then there's also the other black line that's the neutron.
Like here.
So what's the difference between the white or like the boxes that don't have a surrounding that are on the left of the neutron direct line versus the ones that are on the right of the neutron direct line?
You mean
what's the difference between those elements that are not stable, but some of them are on one side of the direct line and others are on the other side?
like here or here? Like
exactly.
before here and here?
Yeah.
Yeah, like if you, okay, the drip line, I think this is a drip line. Let's use this one as an example. Drip line means your separation energy decrease is less than zero, meaning you capture a neutron, you release zero energy. And if you capture further, you don't release energy anymore. Instead, you absorb energy. So the nature doesn't want to do that because they want to stay in lower energy. And this is the last point in this S-particle chain. When you capture a neutron, you still release energy. So that's why after this point, you cannot go further anymore.
Still unstable against like weak beta decays.
Like for those nuclei?
No, the ones on the left.
Yeah, they are very stable. Sorry, not stable. They are radioactive, but they are if we are not in the very end here, if we are here, the neutron capture rates are so much faster than beta decay. So they won't go back. They just capture all the way to the limit they cannot capture. And at that point, because you can only, like everyone is pushing to be here, and the only way to get out of here is to take a beta decay. And then you need to you will form a little bit heavier nuclei. And similarly, a little bit heavier, you will build up in the heavy elements. Yeah, sure.
Where is this happening inside of stars?
I will talk about that. Like, yeah, that's a key question because that's in a very like extreme neutron-rich condition. And where can that happen in the universe? That's obviously cannot happen in our solar system. Yeah, that's a big question in our field. We don't know yet. We don't have a clear answer yet. And that's been a long-lasting question, but we can get some ideas on that. And as I mentioned, it happens in very neutron-rich condition. You need to create a lot of neutrons. And a neutron star might be one option. And for neutron star, for people who are not that familiar, in the stellar fusion reaction, you remember we have an iron core. And what if the iron has been used up? They not used up, but when that's an iron core and then the iron collapse because there are only like gravity, they don't have the fusion energy pushing forward, pushing outwards, and it collapse, it will explode. And when it collapses, the pressure is so large, it will crush an electron and a proton. Proton is positive, electron is negative. When those two get together, they will convert to a neutron. That will make a star. Like after the explosion, they left a neutron star, which is almost has all of the neutrons in here. It's like a giant nucleus. That's what I was trying to say here. Collapse the iron core, pushes the electron into the nuclear core and convert the proton to neutron. And now you have all neutrons there. And right now, you're still from a neutron star. You're not in a black hole yet because there are still some energy pushing forward. And this energy is the neutron degeneracy pressure. And if it's massive enough and they can still push forward. Even the neutron degenerative pressure cannot hold them, it will form a black hole. But that will be some other story. And for here, if you have one neutron star, that's a source. And what if there is another? Okay, before I say that, I should say, since that's a very dense star, and let's see, roughly 1.4 to 2 solar mass, and in this very massive star, the diameter of this star is only roughly 20 kilometer. And I will show you this figure because every time I hear about neutron star physics, that's roughly the size of the neutron star on the Bay Area. So you can kind of see that. And even a little spoon of this neutron star material, it's as heavy as a mountain, but I can't remember the mountain name, but it's very heavy, just to let you know. Yeah, this is from NASA. And then that's one neutron star. Okay, what if you're lucky enough, you have a companion star that's also a neutron star, and one very extreme neutron-rich condition plus another very extreme neutron-rich condition? Just a neutron, that's not enough because you don't have you don't have very high temperature and high density yet. But if those two neutron stars stay together for a while, they rotate with each other. I will show you this movie. That's the proposed condition where the R process can happen. When like those two stars, that's a binary system, they will rotate with each other and they will get closer and closer with each other. And eventually, if close enough, they will hit each other. Okay, I will wait for a little bit. Hit each other, and then that's an explosive event that will eject many materials around. So the colors here can be density, can be temperature, and I can't remember that. But when those materials are being ejected, and that is the environment, extremely neutron rich, extremely high temperature, extremely dense environment. And that's what people think the R process can happen when I was showing the movie, and all of the nuclear reactions will happening around here and forming the heavy elements. So this is the proposed idea. We don't have an observation to confirm this idea yet for a long, long time until 2017. 2017, there's a observed multi-messenger event, which is the GW170817. And we not only observe the gravitational wave, but also the corresponding electromagnetic field. And for the gravitational wave, you know, when the two neutron stars are rotating with each other, they will release gravitational wave. And there is experts on that, but I won't talk about the gravitational wave more. That's the gravitational part that tells us the source of the gravitational wave is the merging neutron stars. And the later electromagnetic signal tells us what powers the energy we observed on the sky. And to look at in practice, on the left figure, this is the image in the galaxy NGC 4993. And this is the part we have the neutron star merger happen. And this picture is taken like 0.5, like half day after the merger. And the light here is bright and blue. It might be a little bit hard to see, but it's bright and blue. And 4 days after, it has transitioned to red. It is the color transition between the blue to the red that confirms the heavy elements forms. The reason is for the heavy elements, they have very high opacity, which will trap the light. If there is no high opacity stuff, the light will drop quickly. But if there are high opacity elements, when the lights are trying to go out, and the high opacity nuclei will absorb those light or the photons, and it will take longer for them to get away. So that's why you will have a longer and redder component for the light curve. And this process has also been beautifully illustrated by one of the professors in our department, like Dan Kaysen. On the left part, you will see the luminosity evolution, and on the right, you will see the schematic ejecta transition from blue to red. Okay, from here, start from the blue ejecta and then transition to red, And on the left part, there is the first component that is what bright and blue that drops very quickly. And later on, you will see another component, which is red, and it lasts longer and decays slowly. That is the signal for the R process elements. And what we talked about, those elements are formed by the rapid neutron capture process. So this is the first confirmation for the R process that's being produced in the neutron star merger event. Okay, now we've been talking about the astrophysical condition for a while. And what we really want to understand is the abundance pattern in our solar system here. And that's just a zoom in of the R process abundance pattern. The S process part has been relatively well understood compared with the R. So my research is more about the R process elements. And that's the observed abundance pattern in our solar system from the photosphere of the sun and also from meteorites. And there are several characteristic peaks, like the second and the third peak. The first one is the iron peak, and I showed you in the lighter nuclei. And that's the main R process we care about. And the formation of those main peaks are due to the closed shell, which are more stable. Kind of in the middle, that is the rare Earth peak, and which is also very sensitive to the nuclear physics and astrophysical conditions we used in the simulation. And one of the key problem in our field to solve is to understand how this abundance pattern forms. And one thing I should mention is the neutron star merger, we talked for a while, that's one proposed R process site, and it has been confirmed in 2017. But unfortunately, we don't have the spectroscopy information, see which element is being produced. So that's the only observation we have. But many, like galactic chemical evolution study has shown that only with the neutron star merger cannot produce the early observed abundance. So that's saying there might be, or there must be other astrophysical conditions that's also suitable for our process production. And people are also actively working on that, but we don't have a clear answer yet. So all of my study we will my part is to assume neutron star merger is the condition and then do the simulation. Okay, now if we have the astrophysical condition, we assume that's neutron star merger, and then how do we get this abundance pattern in simulation? And what we did is to use the reaction network code, which tracks the abundance evolution from proton to from light nuclei pp chain, the triple alpha reaction and carbon reaction, and all the way to the heavy elements reaction. Those are the reaction network. There are thousands of nuclei. That's a very complex reaction network, but I won't focus that much. But that's the thing we are simulating, which elements are going through which reaction and to form the heavy elements. But once we have that, we need to have the astrophysical condition, what I showed you before, how the temperature density evolves with time. That is the one part. And the second part is the nuclear physics inputs, what is the how much energy you release when you take a beta decay, or how much energy you release when you capture a neutron. And those are the nuclear physics part we also need to care about. And what is the reaction rates? Are they available in experimental data? We don't know yet, but I will focus on later. Assume if we have this available, we can do the network calculation, and then we get the simulated abundance pattern. With this simulated abundance pattern, we can compare with the observations and see if the simulation can reproduce this or not. If we can't, maybe the conditions we are using or the nuclear physics we are using are not correct, and we get constraints from comparing with the observation. And with the abundance, we can also simulate the light curve and compare with the observed light curve and get constraints about those two things. Okay, now I will show you one example of the simulation. That's still the nuclear chart, proton number versus neutron number. And the white dots here are the stable nuclei. Those are the abundance pattern we are seeing for this. And the colors here will show the relative abundances of this system. If I play the movie that's in very like high temperature, high density environments, like the neutron star merger condition. And when I play it, it will go through and show you how the abundance evolves and finally to match with the observation. Okay, those neutrons, those seed nuclei, that's so fast, okay. Rapidly capture neutrons all the way to the drip line and to the drip line. And then let me play this again. Sorry. Okay. Yeah, rapidly capture neutrons, when there's no neutron, they just all beta decay to form the stable nuclei. And that is the simulated abundance pattern from the very beginning, like very light nuclei to the final abundance pattern here. That's one example simulation. And we will study all of the details that's involved in the process and what the nuclear physics we used and how they can decay back to form this abundance pattern. Like here, like, yeah, so that will be a different production site. When I was introducing the whole R process abundance pattern, there is the iron peak nuclei, like iron peak there. For the lighter nuclei, let's say before the mass number is reaching 120, there are different production sites, like quark collapse supernova or some other sites, they form the lighter R process elements. For the neutron star merger condition, they're so neutron rich, yeah, they will all the way to form the main R process. So at here, that's a different production site. And for the neutron star merger, they are mainly producing the main elements. So that's why there is a large deviation here. Yeah. Okay. So we've seen that movie, that's an example simulation. And if we look at the nuclear chart here, we've seen that. Okay, the R process path is all the way like here. I don't have that line, but you've seen that in a very neutron rich part. But the question is, do we have the experimental data in that region for us to use in the simulation? The answer is no. Clearly, because I just show you that the blue line is where we have the data. But the simulation spans all the way to the very neutron rich part. So that means we don't have enough data to use. But to still simulate this process, we need to rely heavily on the theoretical simulation. And for the theoretical, I mean theoretical model for the nuclear reactions, for the nuclear masses, nuclear beta decay energies, that's the nuclear data we need to use for those parts to rely on different theories. And for today, I like those two animations. This one should come earlier, I think, but that's fine. Just to show you the gap between the current available nuclear data to the real simulation reach. Okay, among all of the nuclear properties, like that's everything, like nuclear masses, fission barrier, and beta decay half-life, fission half-life, there are so many properties we use in the simulation. We need to rely on theory predictions for all of those properties. But that's the only way we can do the simulation now. And I will use one example, like nuclear masses, to show how that affected the simulation. And there are a couple of reasons. One is that's the fundamental nuclear property. The second is when you calculate other reaction rates, nuclear masses is the quantity you need to calculate others. So this is the one that will affect almost everything. So for nuclear masses, there are different models to try to predict the nuclear masses in the neutron-rich region. And I will not show that because I'm not modeling that. Instead, due to the computational advantage right now, if you have some data, and machine learning might help you to learn the current data and making reasonable predictions. And that's something I used to learn the nuclear masses. For machine learning, I don't know how much you know about machine learning. I will quickly introduce that. If we have this data here, and that's the available nuclear data, we split them to a training data set and testing data set. And the training data set are shown in black, and the testing set is shown in gray. And since we really want to predict the very neutron-rich part, if we don't have any data points there, it's really hard for the model to learn. So instead, we feed the training points with several theory points, like coming from different theory mass model, just to give our model an anchor to say, when you make predictions and the values are roughly in that range. And using this hybrid training data set, and we feed it to neural network, and then try to minimize the loss function, which are shown here. Once the losses doesn't decreases or stabilize, we will stop the training and make predictions. And here, that is our model prediction compared with the data. And if that's in blue, that's saying the deviation is very, very small. So in general, it looks great, but it's always hard to model the lighter nuclei. There are more structural difference in the lighter one. But since we care more about the neutron-rich part and the heavy part, and right now I think there's no problem for that. Numerically speaking, the root mean square error here is comparable to other models, and those are the theoretical or phenomenological models when they are modeling the masses. And what we really care is about the neutron-rich part here, right? And we want to use the model to learn the current data to make predictions in the neutron-rich part. And I will use one example to show that in this thin isotopic chain, how do we predict the nuclei here? That is the prediction. One thing to mention about machine learning algorithm we used here is it not only give you a single value prediction, it also provides the uncertainty because that's a probabilistic neural network. And so for here, the black triangles are the experimental data, and the dark blue square, that is the mean prediction, and the light blue bars are the uncertainties for each prediction. And that's the matching with data. And for here, that is the prediction from our model. And then we will use the model to do the simulation. But before that, I just want to show how we understand this model. And the machine learning doesn't give you a formula to calculate the masses, and try to understand how the model is working and how the model learns the feature you give them. And we just rank how the model is using different features. And the leading terms are like the macroscopic terms, the proton number, neutron number, the mass number, and added by or corrected by the microscopic terms. And that's one way to understand the model. And then we will use it to simulate the R process. On the left, since we have the masses, we will calculate the separation energy. And the reason we calculate separation energy, which is shown here, is that the photon dissociation rate, which is the competing reaction, that's exponentially dependent on the separation energy. So once we update the masses, we need to update almost all of the reactions. This is one example to update the reaction. And the separation energy look like this. And once that is the reaction rates we need to update. And then we run the simulation. For here, that's two different models. And when we use them in the final results, they will have different simulated results here. And which extrapolation is reasonable, which is not, we don't know. We need to compare with those observables. And on the top panel, that's the solar system abundance pattern. And on the bottom panel, that's the comparison to another R process enriched metal poor star, just to give an extra constraint to compare with. And if we have different predictions for those extrapolation region, we will get a different abundance pattern compared with the solar. As for which extrapolation is the most physical or reasonable one, we don't know yet. We just need to compare with the observation. And if you are reproducing the observation, the physics you are using here might be the reasonable one. But if you couldn't reproduce that, that's kind of giving us a feedback to say, oh, your neutron capture or beta decay rates here might not be physical to reproduce this. So that's how we get feedback from the astronomical observation. And there are several things we can compare with. Okay, we need to compare with the light curve, but before that, I also want to show that once we have those simulated abundance pattern, since you have this amount of abundance for certain nuclei, when they take a beta decay, they will release different type of energy. And here, that is how we propagate the abundances to the light curve by looking at the heating rates. And here, that's showing 3 different channels, and different color shows different channel. And the top panel here, or the top line here, that's the beta decay. And you see the heating rate, that is the dominant one, meaning when you see a light curve or something that's bright in the sky, and that's some nuclear energy that's heating this process. And based on our study here, the leading energy, that's by beta decay. So it's all of the radioactive nuclei, they beta decay back to stable nuclei. And that's the main source for the heating. And the green one, that's alpha decay. When you release a alpha particle, you also release some energy, but this energy is so much lower than the beta decay. And the red one, that is fission, meaning you have a very heavy nuclei, you break it up to two parts and form the lighter nuclei. In this process, you also release some energy, and that is the energy level that's contributing to the heating. For this case, the fission is not as high as beta decay, but for some other conditions, in later time, fission might be the dominating source. But here, that's just one example. Once we have this type of heating, and we do the light curve calculation, and that is the shape of the light curve. And the uncertainties here are coming from the uncertainty in the heating rates. And that's also simulated results. And we need to compare with some observations. And the observation can be compared with the light curve in different color band, or compare with the observations in either our solar system or the metal poor stars. We just get feedback from those astrophysical observations to say if our physics or the nuclear physics inputs are correct or not. So that's kind of the whole story, how those two parts, the tiny nuclear physics and the macro astrophysical observables can be connected with each other, and how the nuclear heating is powering this process. And with this, I would like to end my talk here. And what we covered today is the introduction about the nucleosynthesis, and neutron star merger is one of the possible conditions to form the heavy nuclei. And in that process, different nuclear properties will determine how much elements you can create. And by comparing with the observation, you can give us the feedback about the physics we are using there. Okay, I'm happy to take any questions if there are. Yeah, sure. Heavy elements of forms. Mm-hmm. Not yet. That's a, yeah, I can, okay. Later, after I answer that question about together. For that is a really, really good question. Like, the reason I said neutron star merger is not the main or the only source for the R process is at very early time. Because forming a neutron star, you need a very long time for a massive star to die, to explode. And that's just a single neutron star. You might need to wait another one to be a companion, and then rotate, and then finally collapse. That takes very long time to form the first one. But in a very early universe, there are already R process measurements. So that's saying there might be some prompt source to form the R process. And that's why still people are very interested in collapser, which is subset of subset of core collapse supernova. That happens more frequently than neutron star merger, and that might be responsible for the early creation of heavy elements. And answer your question, for this simulation, we are just assuming neutron star merger condition. If we want to form to add like, okay, I maybe say it this way. For the one simulation, it only forms the pattern. We just scale them up to match with the solar pattern. But to scale them up, you need to consider how many neutron star merger events that happens and how much masses that's being ejected from that event. And we haven't done that yet. That will be like more like galactic evolution related thing. Yeah, but that's a really good question. Okay, the next question from online people is.
Oh, no, I meant can you repeat the audience question so that anyone.
Oh, sorry.
Yeah, I think it was for the answer.
Yeah. So the question is, for the simulation, do I consider the neutron star merger happen rate, or did you add them together, or that's just the one simulation? And my explanation is as what I said. Yeah, that's one simulation. We just scale them up. We haven't considered the happening rates or for each event, how much message that's being injected. We haven't considered that yet. Yeah. Are there any other questions? Yeah.
So you mentioned that you used this hybrid training data set where you included both experimental and theoretical.
Yeah.
And the theoretical predictions were pretty sparse, at least from the plot that you showed.
Yeah.
How did you construct the model such that you made sure that it wasn't just artificially fitting those individual data points? How did you make sure that was consistent with also the experimental data, if that makes sense?
Yeah, that's a great question, actually. That's our first time using a hybrid training data sets. Usually people only trust the experimental part, but the challenge for only trusting the experimental part is you only learn the physics in the experimentally available region. But for the extrapolation, you don't have any constraint there. The same physics might not apply to the neutron-rich part. And there are some, like I said, phenomenological models or some other nuclear theory model. They are not purely feeding the data. They follow some physics rules to calculate, even though they are not perfect in matching with the data, but they follow some physics to have the extrapolation. When we sample those points in the neutron-rich part, we are not seeing that's accurate, but just to let the model know somehow accurate. And to avoid reproducing the model we are using, the theory model we are using. And for those points, we sampled from different theory models. So just to avoid trusting one specific model. Yeah.
Cool, thanks.
Yeah, sure. You have another one? Yeah.
In the very cool video that you had at the beginning, where you had like the element being formed.
Like here?
No, the video, the animation that you had.
Oh. Like this movie?
Yeah. There's a point where there's like a very abrupt jump.
Wait,
Yeah, there,
like
jumps
here?
No, like to the corner.
Okay.
Like a lot of protons appear very dramatic. At least it looks,
Like you mean this? You mean this region, right? Yeah.
It looks like it's growing slowly, and then suddenly, like it jumps all the way to the right very quickly.
Yeah. I think Tanya. So let me show you this movie again. So when they go all the way to the heavy part, they are kind of growing slowly, right? Even though they are going all the way to the very neutron, very like high part, that's the super heavy nuclei I was mentioning. Usually they will fission to the lighter nuclei to fill in the two bright region. And then suddenly they just go all the way back to stability, right? The reason is before they go back, the decay rate is always fast as I showed. But before they reach there, the neutron capture is even faster. You want to go back? No, I want to capture, because the capture rates are faster than the beta decay. And why the capture part is not that?
And also the fission.
Yeah, also the fission. But when you do the neutron capture part, there is also a photon dissociation rate that's against you to go forward, because the temperature is so high. And at early time, that's those two competing process. And then you go slowly to the neutron rich part, to the heavy part. But as the temperature drops, the photon dissociation rate drops a lot. And also the neutron capture rate, because you run out of a neutron. And those two reactions just dropped, but you are still piling up there. And then the beta decay start to show up. They just all take you back to stability. That is the whole process. Okay. Yep. Thank you.